All right, who's excited about maths? Yay! Yay!
I am.
Awesome. Awesome. So first I want to give you just an idea of what we're going to be covering over the next 6-7 weeks. So the discrete maths test is at the end of May. It's about a month away or so, a little bit more. It's I think we talked about the 29th that week anyway, 29th of May being when we have the test, okay? So between now and then we're going to cover these 7 topics that you see in Canvas now. Now, our discrete maths lead in Coder Academy has done a really great job of putting together some super fine content in Canvas, okay? I'm going to, especially if you're afraid of maths, I'm going to discourage you from looking ahead at all of the units because it may terrify you. Don't be terrified. We're going to cover each thing in detail and make sure that you're comfortable with it at least to the extent that you can get through the content. So with discrete maths, the reason that we include it in the course primarily is because we offer a Diploma of IT. And in order to meet the learning outcomes for the Diploma of IT, we have to include discrete maths, okay? You aren't going to use most of what we learn here in your everyday actions as a programmer, but some of it is really useful and applicable. And it does, if nothing else, increase and improve your problem-solving abilities and critical thinking abilities and algorithmic thinking abilities. And I think some of you will be happy to know that when we get to big O complexity, we are going to look at some sorting algorithms. Yay! So that's very exciting. But look, some of the stuff that you're going to see if you look ahead in Canvas at these units will look really scary if you're not a maths person. So I look at it and I'm like, ooh, yay. And then you might look at it and be like, what the hell is that? What does that even mean? Do I have to know that? Because I don't think I can. So the test, some of the tests will be really difficult for people who aren't really comfortable with these subjects, but there will be a lot of stuff in there that'll be no problem for you. So remember, you don't have to score 100 on this test. You need to score 50% or better on this test, okay? So keep that in mind as we go along, and particularly when we get to the point of the test and you look at the test. If you're a person like me who absolutely adores maths, then you know, you'll really relish, I think, in these topics, and you'll probably look forward to the test. And yeah, you're weird, okay, but that's, you know, I've totally accepted that about myself a long time ago. The majority of you are going to just like have to suffer through it, but I hope that I can make it at least a little bit fun, because I really do genuinely, authentically enjoy it. If you can't tell, it's a lot of fun for me, so I hope that I can try to make it a bit fun for you. So if we look at the topics, we're going to talk, today we're going to talk about bases or number systems. So bases are something that we use all the time, but we just don't think about it. We don't acknowledge it. We don't consider it, but we actually use it all the time. So that's what we'll cover today. Not tomorrow, but next week we'll talk about logic. Now this is probably going to be one of the easy units for you because we already are using it as programmers. This is one that we use every day as a programmer. This is, you know, if statements, conditionals, all that is Boolean logic. So we're really used to the logic stuff, but we're going to use some terms that maybe you aren't familiar with and some symbols and things like that. Don't be afraid of it. We're going to talk through all of it, and it's going to be fine. Sets are something that really come into play with databases and SQL statements. Right? So unions and intersections, sets are unique sets of things. There's only one element of each type in a set. So when we talk about sets, again, there's going to be some notation there that might feel a little bit scary, but it's just a matter of getting familiar with the notation. We'll walk through those topics slowly. Big O is really relevant to a programmer. So this is considering the complexity of algorithms. And it could be time complexity or memory complexity, how much of a resource is used, and how that resource use increases, the rate at which that resource use increases as the data set increases. That's what Big O is about, is exploring the efficiency and complexity of algorithms. So of course that's really relevant for us, and that's where we'll talk about some sorting algorithms. Matrices, not like the movie The Matrix, but like the two-dimensional array type matrix. This also can get a little bit scary for people because there's some notation that's a little bit scary. There are some operations we can do in matrices that are, sometimes hard for people to swallow, but we're going to take it slowly, and we'll probably spend that lesson. We'll probably, do it in a couple of sessions over the day, just so I don't tire your brain out for those of you who are a little bit challenged by it, but we'll get through it, okay? Graphs is not like coordinate plane graphs. It's like do you know the traveling salesman problem? Have you ever heard of that one? So you have nodes and pathways between nodes, and graphs are generally in the realm of computer science about finding the shortest path between two nodes in a network, basically. So graphs, you think about networks, computers connected on a network. That's another analogy. So graphs are important to computer science, and there's a little bit of notation here too that might be a little bit scary, but we'll go over all of it and get you comfortable with it. Functions and relations are another one that's a bit symbol heavy, and the concepts can be a little bit strange, but you'll be okay with it. So the content again in Canvas for each of these is really good. Let's just quickly look at the content that's in here for today, and we'll go back to it later. So we've got a nice background about bases in here. It's really like a textbook, this content. It's so good. An example of arbitrary bases and everything. There's a PDF that you can download of this too. It's really nice. We talk a bit, there's an Alan Watts quote in here. I love Alan Watts. So that's nice. Binary, arbitrary bases, bigger than 10, hexadecimal, how I learned to stop worrying and love base 16. He's got a bit of humor in here, which is nice. And then there's a kind of fun challenge, I think. It's like a decoder challenge. So you'll just, it's not as exciting as it sounds maybe, but you'll take this string here in hex and then convert it to base 10 and then look up the letters and find out what the message is, right? So that'll be fun. And then in addition to the lesson that I do today with you guys, which I am recording, you can also look at this lesson here that's recorded, and he's just going to describe it. This is an educator in Sydney, so he's just going to describe it a different way, and it might help for some of you to watch that. Okay, so there are some slides for today, and I posted a link in Slack. Did everybody get that? So you can have a look at that link. So let's go to those slides now. And
Janelle,
yes.
Are you able to make the Canvas units public?
Are they not?
No.
Right. Okay. I can. That was supposed to happen already, so so I will do that. I'm not supposed to do that, but I'll just say, oh, we said we were going to do it though. So there we go. Okay, you should be able to see them now. Okay, I got some nice low-res slides here for you. Does everybody have the link to the slides? Okay. All right. So, what is a base? It's one of those little things when you play baseball. There's 4 of them. No, it's not that. It is that, but it's something else too. So you might also see it referred to as a radix. Okay, so if you see the word radix, it's referring to the same thing. It's just the number of digits that a number system has. That's all that it means, is the number of digits that a number system has. So we're really familiar with base 10 because it's what we use as human beings, probably because we have 10 fingers. Okay, so actually not probably, because we have 10 fingers. That's why human beings work in base 10, because we count things on our fingers. And base 10 has 10 digits, and that's why it's base 10. So the digits are 0 through 9. Yeah? And we use base 10, from the time that we come into the world, as soon as we start to understand those concepts, and we're all really comfortable with base 10, we don't think about it. Base 10 is also called the decimal base. Now, the most familiar, or one of the two most familiar bases that we'll see in computer science is binary. The other one is hexadecimal. Binary is base 2, so it only has 2 digits, 0 and 1. That's it. There are as many number systems as there are numbers, but most of them aren't practical or needed. But every number system has a different base. So base 3 has 3 digits, 0, 1, 2. Base 4 has 4 digits, 0, 1, 2, 3, and so on and so forth. Okay? So we don't think about that we work in base 10. We just don't consider it. So if we have a number like 123, then we know how to write 123. We know how to say 123. We're all really comfortable with it, right? It's not a big deal. But how do we know it's 123? How do we know that it's 123? Right? You don't really ask yourself. You're like, just because I know, because that's what that number is. So actually what we're doing is we're starting from the right side of a number. We're increasing the powers of the base with each place in the number. So do you remember probably in primary school when you do writing numbers in expanded notation? Does anybody remember that? Yeah?
2 times 10 to the power something.
Exactly. Yeah, and you talk about the ones place and the tens place and the hundreds place and the thousands place. So they actually do teach it to you in school, but you quickly forget it because it's so just every day you use numbers in base 10, so you don't even really have to consider it. But they do try to kind of teach it to you in primary school, and then if you study maths in high school and university, then you may have come across looking at numbers in other bases before. So what we're actually doing here, like Rachel just mentioned, is we're taking the 3 and we're multiplying it by 10 to the 0 power. Now, does everybody know that anything to the 0 power is 1? Okay, so this is a little bit of a recap on exponents. But any number raised to the power 0 is 1. So that's what we call that the ones place. So the 3 in 123 represents 3 times 10 to the 0 power, or 3 times 1. And the 2 represents 2 times 10 to the first power, or 2 times 10. So we have 2 tens. And the 1 represents 1 times 10 squared, or 10 to the second power, or 1 times 100. And so if we write it out in expanded form, what we actually have is 1 times 100 plus 2 times 10 plus 3 times 1. That's why it's 123, right? But we take that for granted. But we're doing this kind of calculation all the time. And we're so familiar with base 10 that we don't really have to think about it. The decimal system, we just move the decimal point right to the left or the right when we're multiplying by multiples of 10 or dividing by multiples of 10. And it's really comfortable for us. But if you break down what we're actually doing, this is how we get numbers in base 10, the numbers that we're used to working with in the decimal system. So let's look at a number in the binary number system. So binary is base 2, or radix 2. And so the only digits we have are 0 and 1. So if we have a number represented 1110, then actually what we have there, if we convert that number to decimal, and because we're familiar with decimal, the way we deal with numbers in different bases is we convert them to decimal, okay, so that it's something that makes sense to us, because we're used to thinking in decimal. So we convert this to decimal the same way that we deal with the base 10 number. But instead of the places being base 10 raised to a power, what do you think they are? base 2 raised to a power, right? That's all that it is. So here, the 0 is times 2 to the 0 power, which again is just 1. And the 1 is times 2 to the first power. And then we have 1 times 2 to the second power and 1 times 2 to the third power. It's exactly the same as what we do in base 10. It's just that the base, the number that we're raising to a power in each place, is the number for that base. So in decimal, we put a 10 there. And for binary, we put a 2 there. And that's what we use. So here, in this place, we have 0 times 2 to the 0 power, which remember, any number raised to the power 0 equals 1. So that's the 1's place in every base. So we have 0 times 1, which is just 0. And then we have 1 times 2 to the first power. And 2 to the first power is just 2. So we call that the 2's place. Right? Instead of the 10's place, it's the 2's place. So 1 times 2 is 2. And then we have 2 to the second power, or 4. So that's the 4's place in binary. And so we have 1 times 4, which is 4. And then we have 2 to the third power, which is 8. So does everybody fairly comfortable with exponents? What does it mean when I say 2 to the third power? Yeah. So it means 2 times 2 times 2, right? And so you just do the math. 2 times 2 times 2 is 8. Now, if you work with binary for a while, you'll get really comfortable with you'll memorize just by working with it so much that the 2 to the it's the 1's place, 2, 4, 8, 16, 32, 64, and then I start to forget 64, 128, 256, 512, 1024. So you'll at least remember the first, up to the 8th place is really easy once you look at it for a while. So if we look at this number that we had, it's 1 times 8 plus 1 times 4 plus 1 times 2 plus 0 times 1, or 8 plus 4 plus 2, which is 14. If we look back at this number again, when I look at a binary number, I just add up, because it's always 1 times, right? That's the nice thing about binary. You don't have to multiply by any, you're always just multiplying by 1. So it's just the value of the place, and you add those up. So we have an 8, a 4, and a 2. I add up 8 plus 4 plus 2. Does that make sense? Okay, so that's 14. 8 plus 4 plus 2.
So 1110.
Yes.
14 in decimal.
That's right.
Seems like it'd just be a lot easier to work with base 10.
Except that...
I love the way you get used to base 2 by remembering the decimal values for each place.
Yes, that's right. That's right, yes. And so the reason, of course, everything that we do on a computer, everything that we deal with in electronics, with electronic technology, is in binary. At the bottom, at the hardware, it's all on or off. It's all 0, 1. It's all signal, no signal. Everything, the most complicated program, is all 0 and 1. You can reduce it down to 0 and 1. It's amazing. It's phenomenal. Yeah?
What about quantum computing?
No, so not in quantum computing. Quantum computing is different because it's not binary. So in quantum computing, it's going to revolutionize the way that we do things because it's so fundamentally different. Binary is fundamental, absolutely fundamental to the way that we do anything with electronic technology and programming. Absolutely fundamental. So when you change that, it is going to completely alter the way that we write programs, that we build hardware, that we solve problems, that we think about problems. It really is going to change things. But for, at least for the foreseeable future, even as we have quantum computing kind of being used in practical situations when it becomes more possible to build things that use quantum computing at a reasonable cost, we're still going to have binary programming around for a long time, right? Because everything in our society right now that's electronically technology based is based on binary, and you're not going to get rid of that overnight, right? So, okay, so that's binary. So let's look at hexadecimal, base 16, because when we start to talk about a base larger than 10, then we're like, but wait, there's only 10 digits in our world. We only have 10 digits. So what are we going to do? And so we just use letters. Okay? So we start with the letter A. And we will use letters up to a letter representing the digit that's one less than the base. So just like in base 10, we go from 0 to 9, right? Base 10 isn't 0 to 10. Base 10 is 0 to 9. Binary is 0, 1. It's not 0 to 2, okay? Because how do we represent 2 in binary?
1, 0.
1, 0. So we have a single digit, and then once we run out of digits, we have to add another digit to our number, right? So in base 10, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Here, let me just, let me do this. I'm going to do this here instead of on the whiteboard because so I can share it. So in base 10, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And once we get to 9, we have to use another digit to represent the next number, 10, right? And so in base 4, let's say base 4, for example, what would our digits be? 0, 1, 2, 3. And how do we represent 4? Yeah, 1, 0. 1, 0. Okay? Because now we have a number with a 1 in the 4's place, right? 1 times 4 to the first power is what this is representing, yes?
Yes.
Yeah? So that's 4. And how would we represent 5? 1, 1. 1, 1 is 5.
I think if we drew it in a table instead of having just a...
Yeah.
Yeah.
Okay,
we
let's do
have
that.
the notation now.
Let's do that. Good idea. Okay, so let's do a few.
It's a little bit to get your head around.
It is. Okay, so if we had base 10, and we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we have to go to 10, right, to represent the next number. And in base 4, we would have 0, 1, 2, 3, and to represent 4, we have to say 1, 0. To represent 5, 1, 1, because that's 1 times 4 to the first power, 1 times 4, plus 1, which is 5.
Oh,
Yeah?
yes.
And then to represent 6, it would be what? 1, 2, not 12, but 1, 2. To represent 7,
A baker's dozen.
yes, to represent 7, it would be 1, 3. What about to represent 8?
2, 0.
Yes, exactly. 2, 0. Yes.
You're multiplying the second by 4 by 2.
That's right. That's right. Because 8 is a multiple of 4. Or no, 8 is not a multiple. Yeah, 8 is a multiple of 4. And so we see...
Maths is your favorite subject?
Yeah, I know. Hey, no. I was thinking power for a second. That's why I checked myself. So 8's a multiple of 4. And that's sort of our clue that we need to up that other number too, in my mind anyway. So then 9 would be what? 2, 1, because it's 8 plus 1, right? And then 10 would be 2, 2. And then over here in base 10 we have 11, and in base 4 we'd have 2, 3. That's right, which is 8 plus 3. Because that 2 actually represents 8, doesn't it? In base 4, that 2 represents 8.
What's your next number?
3, 0.
That's right.
Yeah.
That's right. So 12 would be 3, 0, because we have 3 times 4. Yes? 3 times 4 is 12, plus 0. So we'll get there. we'll get there. We'll talk about how to translate numbers in base 10 to other bases in just a minute. So if we look at a number that's bigger than base 10, so base 16 is a common one. Okay, so if we look at base 16, then we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9.
The next one's A, right?
A. And A is 10 in base 10. Okay? And then we have B. Ah.
So when you get up to the 17th number, is it, what would it be? Would it be
0, 8.
1, 8.
It'll be, hold on, let me just make more, let me make her
Let's
rows.
just keep yelling out letters and numbers until we get it right.
The 16th number.
Oh, see, that's fine. 13, 14, 15, 16, 17. Okay, so C, so 13 is D, 14 is E, 15 is F. Now 15 is the number before the base, so we stop there. 16 is,
1, 0.
yeah, 1, 0. Exactly. Exactly. And 17 is
11.
1, 1. Yes.
So would you ever get to a situation where you go like 1A or 1B?
Yeah.
Oh, that's terrible.
It's not.
1A would be 16. and
Let's go some more. Let's go some more. Hold on.
It'd be easy just to do base 10. I don't care.
Stop it.
Can't do base 10.
That's right.
It doesn't divide properly.
Have you got enough symbols
Okay, so we got up to 17, and we have 18, 19, 20, 21, 22, 23, 24, 25, 26. Okay. So then,
Can you instinctively, like in your mind, convert, like if somebody says what's a certain number in base 2, are you able to immediately?
it depends on how big the number is.
Oh,
So
yeah.
if it's
What's 84 billion?
Like 48,
Yeah.
you know, like are you able?
yeah, if it's sort of like less than I have a hard time doing the addition in my head if we sort of get past 64 probably, then, and I'm adding up the numbers, like I'll probably make a mistake if I try to do it in my head.
That's amazing.
So that's what calculators are for, though, you know.
Right.
Okay, so what would 18 be in hex? 1, 2. What would 19 be? 1, 3. 20.
So on and so forth.
Until
1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9. And then 26 would be 1A. All right, let's look. 1A, what are we representing there? It's 1 times 16 plus A times 1. What is A? A is 10. We can look back here to see A is 10. Okay? So it's 16 plus 10, which is 26.
Oh, okay.
Okay? 16 plus 10, which is 26. And 20, guess what 27 is? Yeah. Yeah, 27 is 1B.
So when you would eventually get to FF, you would
Yes.
just essentially carry over to the next one.
Yes, so that's right. So what is the biggest two-digit number we can represent in hex? FF. That is the biggest two-digit number that we can represent in hex. FF.
Don't fail.
So is that why the colors in red are like the way they are?
Yes. Exactly. Exactly. Now, what's the biggest two-digit number we can represent in binary? 1, 1. What is 1, 1? 1, 1 is not 2. It's 3. 3. So the biggest number we can represent in 2 digits, and when you think about computers, we store 1 digit in 1 byte. So the biggest number we can store in 2 digits is 3. But if we represent numbers in hex, the biggest number we can store in 2 digits is FF. What's FF?
255.
255. 15 times 16 plus 15. 15 times 16.
15 to the power of 2 minus 1.
It's 16 squared
Minus 1. That's right.
And always
That's
base
right.
minus 1.
That's right.
It's always minus 1, but it starts at 0.
That's right. Exactly. Okay? So, it's a little bit weird because we don't think about things this way, but it really, if you just do it methodically, then there's nothing magic here. It's all it's all just the number in the place multiplied by the power of that base that's represented by that place. So, okay. So if we have the number B4, it's a number B4. In hexadecimal, it's a number. Right? So B4, what are we representing there?
36.
34.
So it's B times 16. What's B in decimal? 11. 11 times 16. I don't know what that is. I'd have to use a computer.
176.
1
Yeah.
Really, if you
Yeah.
times things by 11.
Plus 4.
If you do the times things by 11, if you get the 2 digits, you add them together. So 1 and 6, add them together with 7, and you put it in the middle. You
Nice.
can do that for any 2-digit number times 11.
Nice.
Why are you an arts grad?
I hated maths at high school.
So B is 11.
Yeah.
So 176 plus 4,
Oh, 180.
27 times 11
180.
is 7. Little 9 in there.
Okay, so B4 in hex is 180 in decimal. Now, we can actually convert. So with any arbitrary bases, when we're not talking about binary and hex, but like base 4, base 7, base 5, in order to convert from say example base 4 to base 7, we would have to convert to base 10 as an intermediary step. So we'd go from base 4 to base 10, and then base 10 to base 7. But with hexadecimal, we can go directly from hexadecimal to binary, or binary to hexadecimal. And that's because one place in hexadecimal is exactly 4 places in binary. Okay? So, and that's because 16 is 2 to the 4th. So, for example, 1111 in binary, the biggest number we can represent in 4 digits in binary is 15. So it's 8 plus 4, 12, plus 2, 14, plus 1, 15. Okay, do you see that? 8 plus 4 plus 2 plus 1. 1, 1, 1, 1 in binary. Because it's 2 to the 3rd plus 2 squared plus 2 plus 1, right? So that's 15. And 15 is the biggest single digit in hexadecimal, right? F. F is the biggest number that we can represent in a single digit in hexadecimal, 15. So because we have that relationship, because 16 is a power of 2, basically, because 16 is a power of 2, then one hexadecimal digit can be represented by exactly 4 binary digits. Okay? So what that means is we can, if we have a hexadecimal number that's multiple digits, like 2D, for example, and we want to convert that to binary, we can actually consider the digits individually and convert the individual digits to binary, and then consider it as one big number. So 2 in binary is 0010. Does that make sense to everybody that that's 2 in binary?
1 to the power of 2 and 0 to the power of 0.
Yeah. And it's sort of a convention that when we write numbers in binary, we write 4 places, but you can understand if it was only written in, it just makes it more clear, right, that we're dealing with a binary number. If I wrote the number 10, what would you think it was? 10.
I'm going to throw something at you in a second.
But if you wrote the number 0010, you think it's binary, right? So you recognize that it's binary. If somebody writes 0010, then you recognize that that's a binary number. So 0010, and then D, what's D again in decimal? 10, 11, 12, 13. 13. And 13 in binary is 8 plus 4 plus 1. Yeah? 8 plus 4 plus 1. 1101. So this you have to work it out at the start, but you'll deal with these, maybe you will, maybe you won't. I have for some reason, so maybe you will too. You'll deal with these groups of 4 binary numbers so much that you'll remember the digits, yes,
How do you
up to
distinguish
15.
between, will there be commas between the sets of numbers?
No,
So how do you just distinguish between...
like
your-
2 separate digits versus 1 digit.
Yeah.
It will generally not be written with a space in the middle. So I'm doing it, it's done like that in the slide so you can see that what's on the left represents the 2 in the hex digit,
Yeah.
and what's on the right represents the D, but you would write it all as one number. So 00101101.
Just reminds you of that Futurama episode. 00100101.
Yes. So this is how we would represent 2D in binary. Now, to translate that into decimal, we still have to do some maths, okay? And it's up to you if it's easier to do big number multiplication or big powers of 2 in addition. So what I mean by that is to change 2D directly into decimal, we would say that's 2 times what? 16. 2 times 16 plus D, which is 13. 2 times 16, which is 32. Yeah? Plus 13, which is 45. Yep. And the alternative, so you could do that math to figure out what that is in decimal, or we can take this binary number we just made and said, okay, this is the 8th place, this is the 16th place, this is the 32 place, right? So I'm adding 32 plus 13, which is also 45. So either way, you've got to do some maths to convert it to decimal, and it just depends on what's easier for you to do. I generally prefer to go, if I'm trying to convert from hex to decimal, I will tend to go, depending on how big the number is. If the number's really, really big, then you have to write too many ones and zeros. I'll tend to go from hex to binary to decimal. Yes.
How come we don't take it a step further and hexadecimal is 16? How come we don't go to 32? We've got enough alphabet letters and numbers.
I don't know the reasons for that. We could look it up and find out. You mean like in computing, why don't we use...
Yeah, if you're saving
It's
space.
going to be related to, I think, bits versus bytes. So I said bytes before, but a single 01 is stored in a bit, and 8 of those is a byte, and that's 2 hex numbers, right? And that's why a lot of things are represented in these 2 hex number pairs, like colors, because that takes up 1 byte of memory. So I think that's why.
So it might not be any more...
I think it has to do with computer architecture.
It might not be any more advantageous to go up.
Yeah,
a step.
to go up. Yeah, I'm not sure of the exact reasons for it, but yeah.
People just don't want to figure out 32 bits. 32
Yeah, maybe.
hours.
So is this clear how we can go directly from hexadecimal to binary? We just take it 1 digit at a time and convert those digits into their binary equivalent, which is just, we just have to deal with, 0, 2, 4, 8, which isn't too hard to do in your head. Okay, let's look at the next slide. Now, how would we convert from decimal to binary? So far we've talked about going from a non-base 10 number to base 10, how we do that, right? And we just multiply the digits by the place, by the number represented by that place, right? And that's how we go from a non-base 10 to base 10 to decimal. But how do we go the other way? How do we go from decimal to another base? So if we have the number 25, for example, in base 10, in decimal, and we wanted to represent that in binary, okay? So the one method to do this, to go, and this is the method that will work for any number system, any base that we want to go from decimal to, is we take the number and we divide it by the base number.
It's native base.
So if we're converting to binary, then we divide it by 2. So if we want to go from base 10 to base 2, then we take the number in base 10 and we divide it by 2, keeping track of the remainder, and we do that until we get down to the point that we only have digits for that base.
Why are we keeping track of the remainder?
So this is
Where does the remainder go?
the remainder actually tells us what the number is in base 2. So what we do is we start with 25 divided by 2, which is 12, with a remainder of 1. Yeah? And then we take the answer from that division and we divide it by 2, which is 6, with a remainder of 0. And then we take that quotient, 6, and divide it by 2, which is 3, with a remainder of 0. And then we take that quotient, 3, which is still bigger than 2, right? Divided by 2, which is 1, with a remainder of 1. And once we get a quotient that is less than the base, we stop. Because we can't divide 1. We can't say 1 divided by 2 without getting a decimal number, right?
So in the beginning, when 25 divided by 2,
Yes.
that's 1 because
The remainder's 1. So we're keeping track of the remainder.
remainder is 12. Like as in,
So 12 is the answer to the division, the quotient, right? 25 divided by 2.
oh yes,
Right?
beg your pardon, yes.
Yeah,
sorry, yes,
it's
yes,
12,
sorry.
but it has a remainder of 1. Yes?
Yes.
So we keep track of that, and then we write the number starting from the last quotient and adding on the remainders. So the number in binary is 11001.
So you just sort of write it backwards.
Yeah, we write it backwards. Okay? And that's how we convert any decimal number to any other base. If we wanted to convert 25 to base 4, we'd do it exactly the same way. Or to base 16,
So
Or-
how would you?
to base 8.
How, like if you've got like a really huge number, say 1,000,
Mhm.
change that to base 16, for
Yeah.
example. I'm assuming that you would have to fit in a few alphabets in there.
If we were going to 16, yeah, there would be some letters,
So
probably.
how,
Yeah. So let's try, I think I have a base 16 example in here. Yeah, let's look at this one. But this one doesn't have a letter in it. So if we had the number 356, then we'd start from 356 and divide by 16, which I would do on a calculator because I'm not good at that kind of mental math. We get 22. And then you say 22 times 16 and subtract that from 356 to get the remainder. Yes. So it's 22 with the remainder of 4. So then we take the 22 and divide it by 16, and we get 1 with a remainder of 6. So that in 356 in hexadecimal would be 164. So we would get a letter in there if our remainder or final quotient was larger than 10 or larger than 9. Right. That would put a letter in it.
Why do we have the last one?
Because the last one represents the last division that we can do. We have to represent that. So that's like the last power of 16.
Okay, so the last number of any division will be the first number.
Will always be the first number.
And then it's just like the range.
Yes.
Okay.
Okay? No, you can write, and I think I have it as a morning challenge. I'll give it to you next week to write something that converts from decimal to.
Good a week after we forget about it.
Just to have you practice a little bit. So you can write an algorithm for this, couldn't you?
It'd just
You
be
could write.
mod.
Yeah, you could write it. That's right. So you'd be doing the mods. You'd be storing those, right? You can imagine you'd be sticking those with unshift because the first one you actually want to be the last number, right?
Yeah, so you just have to
So just unshifting in the array to add each remainder until you get to your last division, and then you store that last quotient.
Would you have to do it recursively?
You don't have to do it recursively. You can do it iteratively. Yeah, you could do it either way. Yep. So you can write your own base calculator. See, that'll be fun, won't it? That'll be fun.
Hard enough time to try to write Roman numeral calculator.
A Roman numeral calculator.
Like
Yeah.
convert Roman numerals into decimals.
Into decimals, yeah.
Yeah,
Yeah.
because you got to take account
It
the
does.
letter beforehand, like 9.
It does, yeah. See, this would be easier. This would be easier than that.
There's a logic to this.
Yeah, that's right. Now I'm going to show you a different way. You can ignore this part if you want to, but this is the way that I like to convert from decimal to binary. Okay? Just because binary, the multiplier is always 1. You know, like the digit in the place is always 1 or 0. It's 1 or 0. So what I do when I convert from decimal to binary is this way. So, for example, if we have the number 25, you think about what is the largest power of 2 that divides into that decimal number. So we have powers of 2 are 2, 4, 8, 16, 32. Yeah? So the largest one that divides into 25 is 16, 2 to the 4th. Yes? So what I do is I put a 1 there, and I put blank spaces for everything, all the other places down from that place. And then I subtract that 16 from 25, and that gives me, what's 16 from 25? 9. Yes. So then I asked, does the next lowest power of 2, which in this case is 8, does that go into 9? It does, so I put a 1 there. Okay, and then I subtract 8 from 9. Because now I've taken care of that 8. Right? Now I've taken care of 16 and 8. So I subtract the 8 from 9, and that leaves me 1. And 4 doesn't go into 1, so I put a 0 there. 2 doesn't go into 1, so I put a 0 there, and then I put the final 1. So for me, it's easier to go from decimal to binary this way than doing the division way, and it takes up less paper. Okay, so you could do it either way. This one's harder to code. If you're going to write an algorithm to do it, I would do it the other way because it's generic, number one, and because this is harder to code. Okay, I think that's the end. See, that wasn't too bad, was it?
That was just basis.
That's all. Yeah, and that's all we're going to talk about today. So let's look at.
Can we do a bit of practice?
Yeah, absolutely. So let's look at the Canvas content.
Another way
So-
to do that last conversion is convert your decimal to hexadecimal first,
And then go into that.
and then convert the hexagon.
Yeah.
Then you can just do it one fixed digit at a time.
That's right, and that would be faster for a small number like 25.
Yeah.
Because converting 25 to hex wouldn't be too hard, right? So 25 divided by 16
One.
goes once. Yeah, with 9 left over. Is that right? 9 left over. So it's just 1 9.
9.
Yeah, and then convert 1 9 to binary is 0 0 0 1, 0, 0, 0, 1, 1, 0, 0, 1.
Okay, we need practice.
Yes.
Why did it say 1101?
Oh yeah, it shouldn't. 1, 1, 1, 0, 0, 1. Thanks. No, thank you. Thank you for that. That was my bad. Okay, so let's have a look at what's in Canvas. So there's an interesting thing here about about base 60, because base 60 is sort of what we use for time. Not exactly, but kind of what we use for time. So, yeah, not exactly, but kind of. So we have 60 seconds in a minute, 60 minutes in an hour, but then we have 24 hours in a day. So that kind of screws the whole thing. But 60 seconds in a minute and 60 minutes in an hour. So we don't say if we're talking about, we don't say it's 460. We say it's 5. We go over to the next number, right? When we get to 60, we loop over to the next number. So we sort of use base 60 for time. So there's this bit that's just sort of kind of interesting about base 60. And here there's a talk about how we talked about the base is the number you never reach in the digits for that base. So for example, here's our base 10 compared to base 4, right? So in base 4, there's no 4 digits. There's only 0, 1, 2, 3. In base 7, it's 0 through 6. In base 9, it's 0 through 8. So we never reach the number of the base and the digits, right? We roll over to 1, 0 once we get to that base number. Okay, arbitrary bases are bases that are smaller than 10. And I talked about how if we want to go from, say, base 4 to base 7, let's look at that. If we wanted to go from, how do we get out of this? There we go. Okay, so if I have a number, say 17 in base 10, and I want to represent that in base 4. What is the process that I follow to do that? Do you remember? So 17 in base 10, what do I have to do?
Divide.
Yeah, divide. So I start with 17 divided by 4, which is 4, remainder 1. And then I say 4 divided by 4, which is 1, remainder 0. Yep? 1, 0, 1. So it's 1, 0, 1 in base 4. Yep, and we can double check that and say what we've actually written there is 1 to what? 1 times what? 1 times 4 squared, 1 times 4 to the second, because remember the first place is the 0, 4 to the 0 place, the 1's place, then it's 4 to the first, and then it's 4 to the second and the third place. I'm just going to make my font bigger.
Is the base number just the number you divide the original number by?
Yeah, when we're converting from base 10 to that base,
It would be 17 divided by 10.
no, from base 10 to base 4, then we divide by 4. If we were going base 10 to base 7, we divide by 7. If we were going base 10 to base 8, we divide by 8. Base 10 to base 16, we divide by 16. Okay? So 101 in base 4 is the same. If we write it in expanded notation, right, is 1 times, this is going to be a pain, to 4 to the, are you okay if I write it like this? 4 to the second power plus 0 times 4 to the first plus 1 times 4 to the 0. Yeah? which is the same as
8
8 plus 0 plus 1. No, that's not right. 4 squared is not 8. 4 times 2 is 8. Is 16. I was like, wait, that's not right. That's okay. No, I went right along with it. I'm like, yeah, 8. It's totally 8. It's totally 8. 4 squared is 16. No, that's all right. And 16 plus 1 is 17. So we got back to the 17 in base 10. So you can check yourself at first. If you're not sure that you're doing it correctly, then you can just go backwards in the other direction to make sure you end up with the same number. Okay, so it's 101 in base 4. Now, if I want to say, what is that in base 7? If I started with 101 in base 4, let's do it a different way. So let's say we have 1, 2, 3 in base 4. And we want to know what that is in base 7. What would we have to do first?
Can we convert to decimal first and then convert to...
That's exactly what we have to do. Yeah. So how do we convert it to decimal?
So go through that process of dividing it. Is it? No.
From 4 to decimal, we do what we just did here, don't we? We just expand it.
Oh.
Yeah? We just expand it. So 1, 2, 3 in base 4 is equal to 1 times what?
4 to the power of 2.
Yep, 4 to the power of 2 plus 2 times
4 to the power of 1.
4 to the power of 1 plus
3 times
3 times
power of 0.
just 1. So that's the same thing as 16, yeah? 1 times 4 to the power of 2 is 16 plus 8 plus 3, which is,
27.
yeah. Okay, and that's base 10, yeah? And then we can go from 27 base 10 to base 7.
Oh.
Okay? So how do we do that?
So 27 divided by 7,
Mm-hmm.
which is 3 remaining 6.
Mm-hmm. Are we done?
No. Well, yes.
We are, right?
So, like, so 6, right? 6, 3. 6, 3.
3, 6. And let's just double check that. So 3, 6 in base 7 would be
3 times 7 to the power of 1 plus 6 times 7 to the power of 0.
which is,
21 plus 6.
yeah? So if you do a few examples like this, you can see why that division trick, that division process works. Yeah? Why that produces the results. Yeah? Okay? So it's a two-step process to go from one arbitrary base to another. We have to go to base 10 first in the middle, and then go to the other base. You just take your time with it. Double check your work, you know, or write yourself a calculator and code, you know. So you can write yourself a calculator and code that goes each way. It's not too hard to do. So we'll do that as morning challenges, because then you can just use your calculator and not have to get out the paper. And
I'm pretty sure in Ruby, if you, for an integer, you go .2i and then bracket.
You can.
Base, you can also do it that way.
You
Not that
can.
you learn it that way.
yeah, yeah. So it's good to write a calculator, because then you're going to know that you understand the process to convert from one base to another, right? So it's a good exercise to do that. And then once you do that, if you want to use Ruby's converters, then use Ruby's converters. But you know, every language probably has a converter, I'm sure. But it's good to write one yourself so that you understand what's happening.
What about negative numbers?
Negative numbers will be the same. You would just retain the negative or positive attribute of that number.
And floats?
Floats are different.
Well,
Yeah, let's not go there.
So size in the same process, like,
All right, so bases larger than 10. So
because it'll be negative powers if you go into floats.
if you go into floats, yeah, we'll have some negative powers. Yeah, I don't think I've ever done that in any course, so maybe it's just not useful. Yeah. Okay, so look, any base, it works exactly the same way. These processes that we just looked at, exactly the same for any base. Okay, so there's no magic there. Here's a bit about hexadecimal, and we've talked about this. So this talks about how using hex, like I mentioned, is a way to sort of write binary in a condensed form, so we don't have this like long string of ones and zeros. It can be easier to look at those numbers represented as hex instead. Colors are represented in hex in computing. So you'll see strings with the hash symbol followed by 6 hexadecimal digits. And what that represents is the first 2 digits are the red value, the second 2 digits are the blue value, and the third 2 digits are the green value for that number. Okay? And so for example, teal is 2A, 7A, 72. So the red intensity value is 2A, the blue is 7A, and the green is 72. And that number altogether, represented altogether, represents the color teal. Okay, and that's how colors are represented. So you might see them represented with a hash symbol like that, especially when we're looking at colors, or you might see them of this other form with a 0x in front of the number. That also signifies that it's a number represented in hex. Okay? So here are some things that you can try. So I'm going to let you try these and then we'll look at it together later. So 127 base, I think that's supposed to not be, maybe it's meant to be like that. What's 127 base 10 in decimal? It's 127. I don't know if that's a trick question or if he meant to put a different base there. 6F base, that doesn't make sense. That's got to be 16 because there would be no F in base 15. Why not? Why would there be no F in base 15?
Because you always take one less than your base.
Yeah, so let's assume that he meant base 16. I'll make a note that I need to update this on Canvas. Okay, and then there's some questions like, what's the largest value you can represent with a byte? So a byte,
How many digits in a byte?
a byte has 8 binary digits. Or 2 hex. Maybe. I don't know. Yeah. So a byte can only store a 0 or a 1, right? I mean, not a byte, a bit, sorry. A bit can only store a 0 or a 1, and a byte is 8 bits.
And 4 bits is called a nibble.
Is that a dad joke?
Do you know why?
Is that real?
Yeah, that's real.
Oh, okay.
You know why? You know why it's called a nibble? Because it's half a byte. Yes, nerds do have a sense. A very bad one, but yeah. No, that's real. I didn't make it up.
Okay, so the largest value you can represent with a byte would be what? In binary, what would it be? 8 bits? Yeah. Yep, 255. Yeah, 255. So in binary, that would be 1111, 1111. Yeah? 11111111. In hex, it would be what? F,
For 8 digits as well.
FF. No. So in hex, it would be 11111111 in hex, which is FF. Yeah. FF. And in decimal, 255. I don't know how to tell based on a hex value what a color would look like.
Yeah, that would be.
Understand intensity with the red, blue, and green and how they interact in your head.
I don't. No. I know. I'm just weird like that. Yeah. So if we convert it to hex, how would we convert this to hex? So 247, these are decimal values. 247, yeah. So 247 in hex, yeah?
Why is the color thing green and not yellow?
Yeah, it's a good question that has to do with color theory, and I don't know the answer to it. It's color related to color color is light versus color is pigment.
Yeah, you can't go by colour. Like colours, it's light colour. It works differently.
Yeah.
The physics is different. Also, why is it red, blue, green? It should be red, green, blue. Surely.
I think it's red, blue, green.
RGB.
No, it's RGB.
It's RGB.
Yeah, red, green, blue is the correct order.
Well, let's confirm that. Red, green, blue. Another error. What is he doing?
Webcam, I guess.
Green, blue. Okay. Oops. What happened? Green, blue. All right. So yeah, it should be red, green, blue. There you go.
So that colour would be probably a pale orange, I'm guessing.
Yeah.
Yeah.
We should try it out.
Just I looked up.
Yeah. Red,
Just
green,
by
blue.
looking at the
Okay.
value.
So what are the hex values for this one?
So does that mean
247, 85, 49. 247, 85, 49. Okay, so yeah, we divide by 16. 247 divided by 16. What is that? Somebody tell me with a calculator.
15
Is it 15?
with some kind of remainder? Let me just see.
So that's F, right?
So the remainder 7.
Okay. So then it's, what is this number in base 16 then? It's F7, yeah? 15 times 16 plus 7. Yep. And 85 is what?
5 from 85.
Okay.
Actually.
I don't know. I'm trusting you, Matt.
Yeah.
Yeah? Okay. I don't do this kind of math in my head really well. So 49 divided by 16.
3 with some kind of remainder.
1. So 31. So the hex number, or the hex representation of that color is F7 5531. What's the quickest way for us to see what color this is? What tool?
Google colors.
Actually, just paste it into Google. See if it does.
Yeah.
Oh yeah, that's a good idea.
Because it does everything else.
It does, right?
Oh, look at that.
Look at that. There you go.
Orange is the same.
Yeah.
Do you guys want me to just look at this number and just really visualize what color it is?
Yeah, I can't do that. I'm not familiar enough with.
Just like reading a book and the color was 755.
Yes.
Oh, it was orange. That exact shade.
Okay. This also, there should be an R here.
Yeah, I've done web for so long that I just know it now.
You know every single colour.
Yeah, I can just look at, particularly if it's in hex.
Okay,
I
so
can just look at that and go, yeah, that's roughly that colour.
why don't you guys have a go with this challenge? So this challenge is you take this number in hex, convert it, each one of these pairs to decimal, and then find the corresponding letter or symbol in this table, and then find the secret message. Yeah? Cool.
Oh, that's a good one.
So,